Hello. This is a video on the Euclidean algorithm and more on linear combinations and divisibility. This is a number theory video. In the past videos, we talked about linear combinations, but this is a very central concept here in number theory, so I want to look at it again. Let's go back to page 14 of our book and look at Theorem 4. Theorem 4 is a 3-star theorem in our book. We have integers, of course. We work with integers 99% of the time in number theory. And we know that C divides A and C divides B. That is, C is a common divisor of A and B. Our conclusion is that C divides a linear combination of A and B. Very important theorem. So I'd like to look at some linear combinations. And let's go ahead and use our exploratory question that we asked in week 3. 8 and 20. Consider the linear combinations of 8 and 20. What is the smallest positive number that's a linear combination of 8 and 20? And what is the set of all linear combinations of 8 and 20? So what I'd like to do is go to Desmos and do some exploring. So here we are in Desmos. So let's take 8 times 1 plus 20 times 1. Very simple linear combination. That's 28. Pretty simple. Let's duplicate this a few times. And we can get 28. If I take 8 times negative 1 plus 20, I get 12. If I take 8 times negative 2 is negative 16 plus 20, I get 4. And I believe that 4 is the smallest number that I can get. Let's see if we can achieve 8. We can achieve 8 by taking 8 times 1 plus 20 times 0. So I can get 4, 8, 12. Let's see if we can get 16. Is there some way we can get 16? Well, 8 times 2. Let me duplicate this here. 8 times 2 is 16. I can get 20. I can get 24. I can also get the negatives of these. So for example, let's duplicate. Let me see if I can copy this here. If I take 8 times 3, that's going to be 24 plus 20 times negative 1. Oops, sorry. I wanted a negative here and a positive here. This will give me negative 4. I can get all kinds of negatives here. Let's duplicate this here. 8 times negative 4 would be negative 32 plus 20 would be negative 12. So I'm getting 4, 8, 12, 16, and so on, and the negatives. I can also get 0, of course, if I just take, maybe this will be my last example here. I'll duplicate this. If I take 8 times 0 and 20 times 0, I get 0. Okay, we like extreme examples in mathematics. If the extreme examples don't work, we might be in trouble. We did have someone give a pretty good answer here. Let's go ahead and write down the answers. For 8 and 20, the smallest positive number is 4, which is the greatest common divisor of the numbers. In fact, that's going to be a theorem that we're going to be looking at again. And the set of all linear combinations, ... -8, -4, 0, 4, 8, 12, the multiples of my greatest common divisor. And in the case of 8 and 11 are relatively prime. So the smallest positive number that is a linear combination of 8 and 11 is 1. And the set of all linear combinations will be all the integers. We might jump over to Desmos and make sure that we can get 8 and 11 as a linear combination. Here we have it. 8 times -4 plus 11 times 3 is 1. This shows that they are relatively prime. There will be other linear combinations that give 1. So I hope you're seeing that linear combinations are key here. Now I'd like to go forward. This theorem 4 is a 3-star theorem. Now I would like to go forward to Bezout's theorem. Theorem 9 is Bezout's theorem. This is a 3-star theorem in our course. The greatest common divisor of two integers, a and b, not both 0, is the least positive integer such that we can write a linear combination of a and b. ma plus nb is equal to d. And if they happen to be relatively prime, the greatest common divisor is 1, then I can write ma plus nb equals 1. One more little reminder from our practice homework in week 2, kind of a trivial looking tool, but a useful one. Number 10, if we have integers and we have a dividing b, then a is going to be dividing quote unquote larger multiple of b. This is a pretty obvious fact, but typical of mathematics, we often use obvious facts, easy facts to build other facts. Now I'd like to get into the Euclidean algorithm. The Euclidean algorithm is named after Euclid himself, our great Greek mathematician. And we might have somebody look up, maybe somebody took the Math 406 class here at WIU and can tell us a little bit about Euclid. This is a great method for finding greatest common divisor. Now we've had some other methods in the previous video, the listing method, the prime factorization method, and those are good methods, but this is a very good universal method for finding the greatest common divisor, especially when prime factorization might be kind of hard. Here are the 3 steps. You take your 2 numbers, you divide this smaller number into the larger number and get a remainder. Then you divide the previous remainder into the previous divisor, getting a new remainder. Then you repeat step 2 until the remainder is 0. When you get a remainder of 0, you are done. The greatest common divisor is the last divisor, which is also the last non-zero remainder. Now we're going to need to see an example of this. Let's go ahead and do this first example. Find the greatest common divisor of 70 and 94. Okay, This process is not overly difficult. However, it is something new, so you will need to practice it, and you need to be able to check. So I'm going to take my small number, it's going to be my divisor, and I'm going to put my large number on the inside. And we need to do the long division. Please do not put a number above the 9. 70 does not go into 9. 70 goes into 94. So we put a 1 here, we multiply, subtract, and we get 24. And this is a good remainder because the remainder must be less than the divisor. So we get one remainder, 24. Now we're ready for step 2. The new divisor is the previous remainder. The previous divisor moves on the inside. The way I visualize this is 70 was on the outside, and it's an osmosis where it passes through the cell membrane, it goes underneath. 24 goes into 70 twice. Multiplying, I get 48. Subtracting, I get a remainder of 22. Sometimes this process can be completed in just a few steps. Sometimes it takes a handful of steps. Lather, rinse, repeat. My remainder comes on the outside. The number that was on the outside morphs to the inside. 22 into 24 goes once. I get a remainder of 2. The remainder comes on the outside. 22 goes on the inside. And 2 goes into 2 once. Bring down, 2 goes into 2 once. And I do get a remainder of 0, and it's one of my traditions. I like to make that a smiley face. So this divides in evenly. Now you do have to be careful writing your answer. If you look at the top of your sheet, you'll see what the greatest common divisor is. The greatest common divisor of 70 and 94 is 2. It's the last non-zero remainder, and it's the last divisor. Now that does check. If you divide 2 into 70, you get 35, and 2 into 94, we get 47, and there is no common divisor. A common mistake is to take the last quotient, and that is incorrect. It looks like I have a typographical error here on my handout. This should be 221, and this should be 544. So now let's try to do this with 221 and 544, and if you can be one step ahead of the professor, that's great. Okay, let's find the greatest common divisor of 221 and 544. By the way, in greatest common divisor, it doesn't matter if you put the big number first or second. It's symmetrical. So I put the big number inside on the long division, and that is important. It looks like it goes in twice, getting a remainder of 102. 102 becomes my new divisor. 221 is my new, I believe that's called the dividend. This goes in twice. 2 times 102 is 204, giving a remainder of 17. 17 is my new divisor. 102 on the inside, and 17 into 102 goes 6 times. 6 times 7 is 42. Carrier 4 is 10. Bada bing, bada boom. We are done. We got the GCD very quickly in this case. My conclusion is that the greatest common divisor of 221 and 544 is equal to 17. Now, the next thing, not only is the Euclidean algorithm nice for finding the GCD, but it can also be used to find the linear combination. And here are the steps for writing the GCD as a linear combination. Write the result of each division as an equation. By the way, we're using the division algorithm. You can look up the division algorithm in the book. We solve each equation for the remainder. Start with the second to the last division. You don't need to use the very last division when the remainder is 0. Start with the second to the last division and work backward, substituting for the remainders. Simplify as you go until you get back to the beginning and you'll have a linear combination of A and B. Let's try that on this example. And I think I'm going to switch to a different color. Okay. And this is our division algorithm. It's the check from elementary school. 544 is 221 times 2 plus my remainder. If I solve this for the remainder, I get 102 equals 544 minus 221 times 2. My next statement says that 221 is equal to divisor times quotient plus remainder. If I solve this for the remainder, I get 17 equals 221 minus 102 times 2. Now we're going to be substituting for the remainders. Now I'm substituting for the remainders. I have 17 on the left-hand side of my equation. I want to keep it on the left-hand side of the equation so that I have 17 as a linear combination. I'm substituting for the remainder. The remainder here is 102. So I'm removing 102, and in its place, I'm putting 544 minus 221 times 2. Now I'm going to be using the distributive property. So I will have 17 equals 221 minus, and now I'm multiplying through by 2. 544 times 2 minus 221 times 2 times 2, which is 4. Now I'm going to be distributing the minus sign through. So I have 17 equals 221. And when this negative sign gets distributed through, all the signs change. So we have 544 times 2. By the way, don't multiply these out. Leave them factored. Plus 221 times 4. Now, how many copies of 221 do I have? I have 1 copy in front and 4 copies back there. So I have 5 copies of 221. Whoops, not 222. Get my eraser. 221 times 5 minus 544 times 2. And you want to check this on a calculator, and it does check. You can write the answer this way, or if you would like, you can use a -2, 17 is equal to 221 times positive 5 plus 544 times negative 2. I have written the greatest common divisor as a linear combination of the numbers. Now let's go back and do it for our first example. Okay, we're doing 70 and 94, and the GCD is 2, and we want to write 2 as a linear combination of 70 and 94. Now, there's some flexibility here. You don't have to do it exactly like I do, but you have to get yourself a pattern that you can replicate. 94 is 70 times 1 plus 24, so the remainder is 94 minus 70. In the second case, 70 is equal to 24 times 2 plus 22. If I solve for my remainder, I get 22 equals 70 minus 24 times 2. And in the third equation, I have 24 equals 22 times 1, which is 22 plus 2. And solving this for the remainder, I get 24 minus 22. Now, ultimately, my building blocks are 70 and 94. That's what I want in my final answer. So I start here at the end and work my way backwards, substituting for the remainders. So I'm going to first of all substitute for the 22. I have 24 minus the quantity 70 minus 24 times 2. And when I distribute the subtraction through, I get 24 minus 70 plus 24 times 3. And now I have 4 copies of 3. 2 is equal to 24 times 3. Sorry about that. Let me correct that error. This should be a 2. So I have 3 copies of 24 and minus 1 copy of 70. Now I'm going to be substituting for 24 because it's my next remainder. So I have 2 equals, now I'm going to put that in the place of 24, 94 minus 70. That's going to be multiplied times 3 minus 70. Distributive property, I have 94 times 3. The good news is you don't multiply any of these out. You always leave it in factored form. So I have negative 3 copies of 70 minus another copy of 70, which gives me negative 4 copies of 70. And if you put that into a calculator, it does check. I have found a linear combination of 94 and 70 to give 2. Now I would like to do a theorem where we're going to be employing Bezout's theorem. Bezout's theorem says, well, Bezout's theorem says it's possible, and the Euclidean algorithm actually does it for us. Theorem 9. The example I would like to do is I would like to prove this statement. And this was our other exploratory question in the past week. And I did have a student give the correct conclusion. We're working with 3 numbers A, B, and C here. A and B are relatively prime. They don't have anything in common other than 1. A divides the product BC. But since A doesn't have anything in common with B, A must divide C. A does not divide B, but A divides C. So let's see how this proof works. We start by saying that we're writing a proof. A and B having a greatest common divisor of 1 means there exists integers x and y such that ax plus by equals 1. There's my linear combination that gives the greatest common divisor. Now, I'm not going to finish this theorem for you. I'm going to let you finish it. But I will give you a hint here that if we multiply through by c, because we do need to introduce c, I'm going to have acx plus bcy equals c. Now we need to have a little bit of room here, leave a few lines available. And we're going to have a few lines available, which I will leave for you to fill in. But I think you do know the last line of our proof. The last line of our proof needs to be our conclusion that A divides C. We have not yet used the other piece of given information. The other piece of given information is that A divides BC. So you're going to need to use that fact. Okay. The last thing I'd like to do in this video is take a look at an example of an always, sometimes, or never question. Always, sometimes, or never questions are very good questions in mathematics. You make a statement and you ask the students, is this statement always true, sometimes true, or never true? And here are the directions in this particular case for the way I'm executing it here in Math 407. Determine if it's always, sometimes, or never true. If it is never true, I'm going to have you give me one counterexample. It might be nice to prove it why it's never true, but one counterexample is going to be sufficient. I'm going to be a little bit lenient. If the statement is sometimes true, give an example where it is true and give an example where it is false. And if you think that the statement is always true, then just state that. A proof would be nice, but once again, I'm going to be lenient and not require that. So here's our statement. I have two natural numbers. The first number, R, divides evenly into B. The conclusion is that R divides evenly into B plus 1. First thing you want to do, it's almost like a true-false question, is you want to try to prove it false. If you can prove it false, that's great. So let's take an example here. All right, so let's say maybe that 3 divides 12. 3 divides 12, so R is 3 and B is 12. Can we conclude that 3 divides 12 plus 1, which is 13? Well, that's false. So this is either never true or only sometimes true. Now we need to see if we can think of some numbers that make it true. So we might think of some simpler numbers, maybe like 2, for example. 2 divides 12. Does that imply that 2 divides 13? No, this is still false. This is false. So now we start looking for extreme examples like the number 1. Let's say that R is 1. 1 divides 12. Is it also the case that 1 divides 13? Yes, this is true. So this statement is sometimes true. So this is kind of my scratch work, and now I'm going to write up my answer. Sometimes true. One divides 12 implies 1 divides 13 is true. 2 divides 12 implies that 2 divides 13 is false. This concludes our video this week on the Euclidean algorithm and a further look at linear combinations and divisibility. We just have the one video, but it's very important in this course. It's very important in all mathematics courses to connect the new material with material from the past. So you may need to go back and revisit some of the notes to make the connections. I want to encourage my Math 407 students here at Western Illinois University to give me a call and or come to my office and or come to the Zoom exchange on Wednesday nights. Have a great day.